We're going to talk about exponential word problems. So please read the following example. Okay, so let's go through it step by step. First, we're going to find the value of b. This experiment tells us we're going to model it with an exponential equation. So here I have the standard form of our exponential function ready to be filled in. So we're told in this problem that a is equal to p sub 0, which stands for an initial population. So that's just telling us wherever a is, we're going to stick it in our initial population. And we know that the initial population is 2300. So we have f of x equals 2300 times b to the x power. The next piece of information we're given is some sample data. It tells us on day 2, the population is 6836. That means we're given the set of coordinates 2, 6836, which we can also write in function notation like this, f of 2 equals 6836. What this is a sample. It says if we put in day 2, we should get 6836. So I'm going to put that in, the 2 for x, the 6836 for y, and now I can solve for b. Our first step is to divide both sides by 2300. When we divide the 6836 by 2300, we get 2.972 equals b squared, and then we can take the square root of that. Now, please realize when we take the square root of a number, we get both the positive and negative answer. We must remember that b stands for our growth factor, which is based on 100%. So here, 172% makes sense, whereas negative would not. Our growth factor is always going to be a positive number, so I can throw out the negative part of that answer and only keep the positive. Part B asks us to write the function modeling this situation. Remember, we had determined before that our initial population was 2300. Now that we know our B, we can create our exponential equation. Question C asks us to find the population on the 6th day algebraically. Another way to say this is to find the population on day 6. Which means we would plug 6 into the formula that we found above. Once we churn that through our calculator, we get the answer. The 6th day population of bacteria is approximately 60,386 bacteria. Question D asks us to graph the function for the experiment time frame. I'm going to use Desmos online graphing calculator to create my graphs. So I'm here at Desmos and I've typed in my function using the keypad that they provide and the mathematical symbols down here. What you'll notice is no graph appears, which actually means that my domain and range need to be reset to accommodate my graph. So I'm going to start by clicking the settings button up here. On the x-axis, remember the x is the number of days. So I'm going to go from -1, just to give myself a little space here, up to 10 days. My y-axis stands for number of bacteria. I know that I started with 2300, so we'll use 0 for the minimum. And we know that our bacteria are growing quickly. By day 6, it was up to several tens of thousands. So maybe we want to go to 100,000 here. And now suddenly we can see our graph appear. We can see our graph down here at 0, where it starts at 2300, and we can see how quickly that exponential graph grows. The next question asks, how can you use the graph in D to verify your answer in Part C? Recall that in Part C we found that on day 6 there should be 60,000 bacteria. If we look at our graph at day 6, we can click right here at day 6, and Desmos will allow us to click and drag along that graph, and we can see that at 6, it gives us 60,386 bacteria. The final question asks, on what day does the population reach 20,000? What we're going to do is we're going to put 20,000 into our function for the population and solve it backwards for x. Here's our original function, putting that 20,000 in for our population. And now we'll begin solving for x. We're going to start by dividing the 2,300. Now that we have this piece with the exponent by itself isolated, we're going to take the logarithm of both sides. It doesn't matter whether you use log base 10 like I have here, or ln, the natural log of both sides, either works the same. Once we've taken the log of both sides, that allows us to bring x down from the power as a coefficient. Now that we have x down on the same level as everything else, x is multiplying times log 1.72399, so we will divide that to the other side. I now have log of 8.69 blah 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 divided by log of 1.72 blah blah blah, and I'm going to run this through my calculator. So my final approximated answer here is 3.97. Remember, we were looking for the number of days for bacteria to reach 20,000, and our final answer is approximately 3.97 days. I hope this has helped you with the idea of setting up word problems that contain exponential functions and how to work with those functions after they're found. Thanks for watching.